Hello, everyone, and welcome to this new episode of AI Talk series with NeuTigers, a show where we explore the benefits of EdgeAI. Welcome to the show, Professor Jha.
Thank you, Stan.
Welcome to the show, Professor Jha. And just what is EdgeAI in a few words?
So let's take a step back before we answer that question. So if you look at Internet of Things, which has sensors, actuators, processing elements, and sensors collect the data and they send it to the edge devices, which are like smartphones, smartwatches, and then the edge devices send the data to the cloud. And traditionally, cloud has distilled the intelligence from this sensor data in terms of machine learning models. And then the cloud sends the model back to the lower levels, to the edge. And ultimately, in this decade, we'll start seeing even sensors getting smarter. So, Edge AI basically is taking these models and making it compatible with the fact that you have energy constraints on your smartphone, although you do have a lot of battery, but you don't want to drain it very quickly. You have memory constraints. In some cases, you may have latency constraints. You have to make the decision very quickly. So, Edge AI basically is making AI, or in particular machine learning, which is a subset of AI, compatible with the edge, with all these constraints that we have to take care of.
Right. So it's computing the AI algorithm on whatever device, whatever Internet of Things device that we are using.
Right. And ultimately, sensors, which are even more battery constrained than your smartwatches and smartphones, would also become smart. By smart, we mean putting a machine learning model, an inference model on the sensor. So suppose I have an arrhythmia sensor. Right now, what it does is it looks at the analog input, converts that into a digital input, and just transmits that to my smartphone. That
Right.
transmission takes a lot of energy. So if you make the sensor smart, then it recognizes in real time that there is no arrhythmia right now, so there's no need to transmit the data, and it saves a lot of energy. So
Okay.
basically, you do AI, do ML under these constraints.
Okay. Thank you. Thank you. And so when I was introducing you, I said that you're a professor here at Princeton University. And I just want to take a minute to recognize that people are logging in from all over the world today. We've got people in Spain, in Austin, Los Angeles, Florida, Boston, Iran. Someone is logging from Iran. Most of you guys are in the US, Philadelphia, Seattle, also Ottawa, Canada, Dallas, Texas. So thank you so much. We've got quite an international crowd today. You are here at Princeton University, but tell us about your role with the university and what is your role at NeuTigers?
So I'm a professor of electrical and computer engineering. I've been on the faculty at Princeton for 34 years. I'm also an associate chair currently. And the kinds of research problems that we look at are algorithms, architectures, design automation tools for AI, for machine learning, with applications to smart healthcare and cybersecurity.
Okay, good. So right now, AI is doing mostly correlation. When do you think that we will be able to add a more abstract layer with more reasoning capabilities, sort of like our brain is capable of doing? And could Edge AI leverage on the AI reasoning application, specifically in healthcare?
Yes, you're correct that most of the AI applications currently rely on correlations. So I have a bunch of descriptive features. I try to correlate it with whatever the target is. And often you'll have false correlations. For example, the sales of ice cream in the summer go up. So there is a correlation, but one doesn't cause the other. Um, and so there are all these confounding variables that may cause false correlations to happen. And that's why AI or machine learning today, which is mostly based on inductive learning, does not give you 100% correct answers. But human beings, if you give us a bunch of axioms, we derive theorems from it, which are 100% of the time correct. So there's deductive learning, which was the focus in the 80s, 90s, but it didn't scale. And currently, the inductive learning approaches, they scale, but they cannot guarantee 100% accuracy. So we need to marry the two. If you want to do higher levels of reasoning, which may involve interventions, for example, when the COVID-19 vaccine was developed, there had to be a randomized controlled trial where there was an intervention. Somebody got a placebo, somebody got the vaccine, and then they had to wait for a few months to see how the two groups fared. At a higher level, we may look at counterfactuals, which does not exist in the physical world in our own experience, but it's a what if question that we are asking. What if this had not been true, something else had been true? We are very good at being able to deduce what would have happened in that virtual world that doesn't exist. And that means we don't require too much data to train our brain. But currently, AI and ML and neural networks, they need a lot of data to train them. So in this decade, we'll start seeing interventions, counterfactuals, working in the low data regime, going beyond correlations. All of that will begin to, it's already happening, will accelerate in this decade.
Okay.
Okay.
And you were talking about the need. Ooh, I can hear my echo here. Let's see if I can fix that. I don't know if it will be. Yeah, it's better, I think. So you were talking about the need of data, a lot of data, right, for the computation. And when we think about computer and artificial intelligence, it's obviously very tempting to try to compare that to how brain works. However, unlike our human brain, deep neural network, they need, as you said, a large amount of data and computational resources for training. What is your approach to that, especially when it comes to EdgeAI? How do you solve that need for a lot of data and resource?
Yeah, so that's a constant tussle. Many applications, smart healthcare, for example, I want to distinguish disease from non-disease, disease from healthy. I need to collect a lot of data, which is not easy to collect. So an alternative, and that is gaining steam also, there are many startups being formed just on the basis of synthetic data. So if you can draw synthetic data from the same probability distribution as your real training data set, and now pre-train your neural network so that it gets into a good place, so that next, when you train it with real data, it gives you very high accuracy. So that's something that we've looked at. We've developed a tool called Tutor, which does that, and others are also looking at the applications of synthetic data so that the need for big data becomes less and less as we go forward.
And so I'm obviously pretty new to AI, but when I read the Tutor paper, I noted that you were sort of mimicking the brain, right? Can you tell us a bit more about that?
Yeah, so there are many ways of mimicking the brain. In fact, if you go back to the 1943 paper, McCulloch and Pitts, they defined the artificial neuron modeled after our brain. We have about 100 billion neurons. We have about 100 trillion connections among those neurons. And so they defined, inspired by the brain, the concept of an artificial neuron, and others took it forward, connected these neurons together, and the concept of an artificial neural network was born. But for the longest time, that's where the inspiration stopped. And so biological neural networks and artificial neural networks diverged a little bit. But now there is feedback that we're getting from neuroscience, and there are neuromorphic architectures that try to mimic the brain. Then in our own work, not just in Tutor, but there is a tool called Nest, which is for image data. There is a tool called Scan, which is for sensor data. The way we mimic the brain is the way our brain develops. So I don't know if you're aware that you were the smartest when you were a toddler. And the definition of smartest here is maximum number of connections in the brain. So after that, it is all downhill for us adults. So from a baby brain, you grow to a toddler brain, and you gain accuracy. You train the neural network by adding neurons and connections to increase its accuracy. But then you're interested really in one particular application. Maybe it's diagnosis, maybe it's cybersecurity. And then you try to reduce the number of connections through pruning, and you get an adult brain equivalent, which is very good for that particular job. Unlike the toddler brain, which is a general purpose learning machine. Your toddler is extremely smart, and you were extremely smart when you were a toddler. So we try to mimic this approach when we combine this synthetic data plus the real data, and then using these two, we want to train and synthesize neural networks that are very compact, very memory efficient, very energy efficient, latency efficient, very compatible with the edge. So that's some of the inspirations we are taking from the human brain in our own work. But there's a lot more going on in terms of inspiration from neuroscience coming back to computer science.
Right. Thank you. Thank you so much. And so to the audience, to everybody listening, if you have any question for Professor Jha, make sure you ask those in the comment. Don't wait until the end. Please go ahead and fire your questions. So Professor Jha, so far we've already been talking about the technology. I would like us now to look at how we apply that concretely in application, software application using that technology. And in here at NeuTigers, and thanks to your work, we've been able to combine wearable medical sensors and machine learning to track and diagnose physiological signals of disease and mental health conditions. We are currently awaiting FDA approval for our smartwatch-based COVID-19 screening solution. And we're also working on various conditions, including sickle cells, diabetes, and, as I said, mental health. Tell us, what is the role of EdgeAI in interpreting sensors data?
Okay, so EdgeAI basically opens up many new applications that were previously not possible. So one of the applications that you mentioned, COVID Deep, which is for distinguishing asymptomatic and symptomatic individuals from healthy individuals. And there, the data collection is from the sensors in your smartwatch. It could be skin temperature, skin conductance, heart rate. It could be pulse, oxygen level, blood pressure, questionnaire. So all of these come together, train a neural network. That neural network can be encapsulated into an app. That app you can download onto your smartwatch or smartphone. And then within a minute, the inference time is just 1 or 2 minutes of data collection. It will tell you whether you're COVID positive or COVID negative. In the lab, we got 98% accuracy. In the field, also, we're getting above 95% accuracy. It is, as you said, awaiting FDA approval. And the hypothesis behind this approach is that any disease, and we've tested it for some of them that I'll describe in a second, any disease leaves a signature on your physiological signals that can distinguish it not only from healthy individuals, but also from other diseases. And so far, we've looked at diabetes, type 1, type 2. We can diagnose that at 96% accuracy. We've looked at, it's a framework called MHDeep, where we looked at schizophrenia, bipolar disorder, major depressive disorder. We can diagnose them also against healthy individuals at very high 90 to 100% accuracy. So, and NeuTigers is looking at other diseases, sickle cell, and we are looking at other mental health conditions also. So this ability to have these sensors diagnose you, and there's a privacy issue that is also maintained. The diagnosis never leaves my smartphone. So nobody else needs to know. So privacy of the user is maintained. So these kinds of new applications are being enabled now that were not possible if you had your machine learning models in a server somewhere in the cloud. Then there will be privacy issues associated with that. Others can also access that health information, and health information is so crucial and private that you really want to control it much better. And this we call it the STAR deep approach. In computer science, STAR stands for anything that you want it to stand for. So
Mm,
it could be diabetes, it could be mental health, it could be COVID. So that is the rationale, the philosophy behind the StarDeep framework.
right. Okay. Um, Thank you so much for your question. So we've got a question about the security of the edge device, and we are going to cover that very soon. Right? Someone is saying that it's very impressive, so thank you so much. Um, all right, so I'm going to read this question, which I don't really understand, but maybe you will, right? And by the way, Professor Jha, you can click on the comment and, to also see the question like I do. In less data scenario, is a few shot learnings be an option?
Yes, so we are very good at few shot learning, which basically means learning from a few examples.
Oh, okay.
And current machine learning models are not very good. They are data hogs. They're not very good at learning from 5 or 10 examples. So, but once we have a machine learning model available, which was trained on a lot of data, now at runtime, you can personalize that to individuals. So suppose you have a diabetes model already developed, and now we have it in our smartphone. That can get personalized with much smaller data. I wouldn't say just 5 or 6 examples, but much smaller data than was used for training purposes. So we are not quite there yet. There are papers on few shot learning, and that is a holy grail, how to come up with models which require only few examples for training purposes. But you can do incremental training, which would be a baby step in that direction.
Okay, good. All right, so moving on. Many of our remote patient monitoring solution vendor we work with come to us for our risk analytics product. How how does data mining, the traditional data mining, is different from AI in helping understand the health risk profile of a particular population?
So when I'm looking at risk, what happens, there's a subset called supervised machine learning, where you assume that it's not just the data that you collected that has been given, but somebody has labeled that data. So, for example, if I'm trying to diagnose schizophrenia, then I collect data from the patient, but the psychiatrist has told me that this person has that particular mental health condition. So that is supervised learning. If you give this data set to me, then I can do an analysis. Basically, I can find correlations between the descriptive features and that particular target. What happens in data mining is you're looking at associations, you're looking at different features, different variables, and you want to see if there are correlations among them. But you don't have the labels associated with those data. So you may want to cluster the data, for example, and assume that whatever data are close to each other, and in a space we call feature space, um, then you assume that they share some characteristic. And there is another, it's like the galaxy that we live in, or the universe that we live in. There are these solar systems that you can think of as a cluster, and there is another solar system far away, which is another cluster. But most of the space of this universe is empty. And so in this multidimensional data space, you have a similar phenomenon where you have clusters of data, these solar systems or galaxies, and the galaxies themselves are far apart from each other. So, if you're just interested in finding out what are the data elements in one galaxy, then you would do data mining. But you have to take a step forward if you want to do supervised machine learning, if you want to do correlations-based diagnosis, for example.
Okay, all right, good. So, as we said all along, at NeuTigers, we are really building solution for better healthcare. However, thanks to your work, we own IPs in other areas. So let's now talk about the telecom and cybersecurity. And I hope we will answer the question that was asked. Uh, so EdgeAI, as we learned so far, is basically AI for the Internet of Things, like smartwatches and industrial monitoring sensors. And we are living in a hyper-connected world, right? I read that there are 50 billions of connected devices at the moment. With new networks such as 5Gs and 6Gs, we are going to connect even more devices even faster. What are, in your views, the new risks in terms of securities and privacies, and what solution uh, did you come up when it comes to edge AI
Okay.
in terms of
If you look at
cybersecurity?
if you look at security at your smartphone level, so a lot of attacks have been in the news where the smartphones get hacked, private information is leaked out, your mic is turned on, photographs are being taken surreptitiously. So, if you look at this problem, to me, there is a lot of parallel between smart healthcare and smart cybersecurity. Both of them currently are reactive and they should be proactive. So, we keep reacting in healthcare. I fall ill, I go to see a physician, hopefully, I get cured. In cybersecurity, there is an attack, then I try to patch it up, and hopefully, I have patched up the system so that there is no further attack of that type. This is all reactive. So what we want to do is make it proactive. So let me just give you an example, and you can see the parallel if I give you this example where the way the malware on your smartphone is accessing your sensors on the smartphone is very different than when your normal applications that you run on your smartphone access your sensors. And you may have 15, 20 sensors on your smartphone, another 10 on your smartwatch. So there is a signature being left by the malware that you could, if you had enough training data, if you had the corresponding labels, you could train a neural network, and the neural network will figure out that currently there is malware of a particular type on your smartphone. So that is just at the edge AI level. But edge AI really serves higher level systems like Internet of Things, like smart cities, your smart home. Everything will have a smart in front of it. There'll be AI seamlessly inbuilt into our environment. Our home will know if I'm thermally comfortable, if I'm secure and safe, if I've fallen ill. The roads will charge up my EV. Smart cities will give us lots of new benefits. Smart grid, smart surveillance, smart everything is becoming smart. And there are, of course, some downsides to it as well, but a lot of upsides. So at the IoT level and IoT device level and then IoT system level, you again have these problems that there are these zero-day attacks where you are surprised. Nobody had ever launched that attack before, and hence you had not prepared for that attack before. So it would be nice if you could figure out, and again, machine learning can come in because our thinking is biased by what has happened. And sometimes we are not able to break out of that bubble, but machine learning algorithms don't have that problem. So we have actually used a system like that where a machine learning model could detect a lot of vulnerabilities in IoT systems that human beings couldn't. And by these kinds of attacks, I'm referring to Stuxnet against Iran. There was a malware, there was a ransomware attack against the national health system of Britain. There was a Mirai attack that came in the northeast of US in 2016. It was a distributed denial of service attack. So there have been major attacks like this, about 40 in the last 40, 41 years, roughly one per year. But our machine learning model could discover about 130 new vulnerabilities that nobody had thought of earlier. So there are other ways in which you can use not just edge AI, but looking at more at the system level of what kind of attacks are possible. And we also wanted defenses against those attacks before we published the paper. And we did find defenses against those attacks. And you mentioned 5G is coming, 6G will be coming in another 10 years. 5G has a lot of software defined networks and control plane, data plane, and the attack surface becomes larger. So it'll be easier to attack 5G. And so we have to be prepared again proactively against the attacks that we have currently not yet thought of. But we should maybe use machine learning to be able to discover those future attacks and take preemptive measures.
Right. This is both very exciting and very scary. So do you imagine having like robots fighting each other, like machine learning protecting a device while other machine learning try to attack that device?
Yeah, I think cybersecurity is an infinite game, and there'll always be new attacks and there'll always be new defenses. It may be robot against robot, and maybe AI against AI. And just like healthcare to me is also an infinite game. The viruses are trying to infect us, and we are trying to protect ourselves using vaccines and other means. That's the parallel that I see between the two areas, and maybe you can borrow some techniques from healthcare domain, apply it to cybersecurity, and vice
Yeah.
versa. There's not been too much cross fertilization between these two areas.
Yeah, absolutely. So we are getting at the end of our interview. Before we close up, I've got a little some comments to make. Let me see if we can take some question here. So we have a question about: do you think that edge AI can be used in industrial application which are not energy or computing power constrained?
Yes, sure. So then you can put AI or ML on a server. If you're not energy constrained, then what you could do is come up with more, bigger and more robust models. So generally, when you make the model bigger, it requires more data to train, but it also typically has higher accuracy. So in the scenario that you just mentioned, higher accuracy would be the prime concern. And so then you would put AI on the server, and then definitely the techniques will be similar. The synthesis of neural networks would be based on similar tools, but you would have bigger machine learning models.
Okay. All right. We've got a question regarding our health monitoring device. What other sensing or sensors are you using other than the heart rate, the temperature, the BP, etc.?
Yes, so I mentioned those are the ones that have been very um, helpful to us in the kinds of applications I mentioned. Another one that I didn't mention, we call it your smartphone understands you. So we want your smartphone to be your best friend. And by that, we mean that your smartphone should understand the physical state, mental state, and psychological state that you're currently in real time. And that is possible. So there, it's not just the physiological sensors that you find in your smartwatches, and more are being added every year, but it's also the sensors you have in your smartphone. For example, accelerometer, gyroscope, and magnetometer. There are also all kinds of sensors in your smartphone that also have weak signals. So each of these sensors gives you weak signals, and they are weak learners. If you just uh, build your machine learning models based on one of these sensors, the accuracy will not be high. But together, these weak learners become a strong learner if you combine them. For example, your skin conductance is a great betrayer of your emotions. If you told me what your skin conductance level is right now, I could tell you what your emotion is right now. So there are different sensors catered to different aspects of the target features we may be interested in, whether it's disease, whether it's your mental state, and so on. But definitely, you have about 25, 30 sensors in your pocket right now or on your wrist. And you can imagine many other applications as well based on data collection from those sensors.
Thank you. Uh, we've got a question about synthetic data. Does the use of synthetic data in your machine learning model increase the risk of biased?
So, synthetic data is only going to mimic the probability distribution of your real data. So, if your real data has bias, then and these machine learning models are very good students. You teach them garbage, they'll learn garbage very effectively. So, it's really, we have to guard against bias in the original real data that we collected. So, it's not synthetic data that will give you the bias, it's the original data that you collected. For example, in images, it has been found that there is a lot of bias, and so we have to guard against that by just collecting data from all uh, different people, not just one set of people. And there's another aspect that is often overlooked. So everyone talks about AI bias, but there is a great book by Daniel Kahneman. He's a Nobel at Princeton in economics, and he's written this bestseller called Noise. So there is a lot of AI noise also. There's a lot of noise just means variance, and bias just means deviation in the mean. So if like when we make judgments, if I'm a judge, I make a different judgment based on the same data than somebody else who's a judge. That's noise, that's variance. If I'm a radiologist, by looking at the same image, I may make come to a different judgment. I may see a tumor or not see a tumor, and the other person reverse of that. So we have to guard against noise, and that's often overlooked. So it's really a balance of uh, how do you reduce bias, but without aggravating noise and vice versa.
Thank you. How important is the development of in-memory computing technology in EdgeAI? Is the memory processor transaction the primary bottleneck today for EdgeAI technology?
Yes. So basically, processing and data, if they are at two different places, I have a DRAM where all my data are, and microprocessor where all the processing takes place. Then I have to feed the processor with data from the DRAM, and that time that it takes to execute that communication may overwhelm any advantage that you have in running on a very fast processor. So this data communication has become a very important issue. So there are other types of chips, for example, monolithic 3D chips. A lot of people are working on that brings the DRAM or some main memory, RAM, some other types of main memory on top of the processing element, so that you have just vertical connections among them, 100 nanometers, and you can feed the data. So that's one aspect. But there are accelerators that people are developing that address this key issue of how do I get the data to where the processing takes place. And right now, this is called a von Neumann bottleneck. This is a memory wall. I cannot get enough data out of the memory quickly enough. So that is a major ongoing effort by the research community to accelerate this communication.
Right. So we are slightly over time, but this is excellent because we had a lot of very, very good questions. Thank you so much for asking those questions. We could go on forever. And, I would love you to talk about neuromorphic, federated learning, digital twins, which are very trendy at the moment. Ethics, ethics is a big topic when we speak about AI. Would you accept another invitation to the AI talk series, Professor Jha?
Sure. Yeah.
Okay.
Yeah. So
Good.
so let's address some of the phrases that you brought up.
You want to talk about them right now?
So yeah.
To me, it was really more the topic of another session. If you want to say a few words, be my guest. But
Yeah, so we are actually working on digital twins where we want to make an intervention. So suppose I'm depressed, and when I go to see a psychiatrist, maybe cognitive behavioral therapy would work for me. Maybe medicine one will work for me. Medicine two will work for me. It takes many months of trial and error to figure out what is the correct therapy for a particular patient. Now, if we could have a digital twin where you have a pre-intervention trajectory, the intervention that took place, and a post-intervention trajectory of data available, and then I go to the clinic and they can collect maybe 1 or 2 hours of data from me, physiological data, and then they have to predict what is the most efficacious therapy for me. So that is within reach, and we are using digital twins to solve that problem. So these are higher level than correlations problems. And so higher levels of learning come in. But a lot of the neuromorphic architectures, they are a separate way to implement neural or machine learning algorithms, federated learning, where you train on a bunch of smartphones. They all have their model, but they have their own data. And then you send some of the gradients to the cloud, and cloud combines them together, sends back the model. So all these ideas are wonderful ideas that the industry is pursuing and academia also is pursuing.
Okay. Excellent. Thank you so much, Professor Jha. That was very, very interesting. That was fascinating. Everyone, make sure you save the date for January 6th at 11 a.m. Eastern Time. We are going to talk about how does AI reduce medical cost and help monitor chronic disease with our CMO, Gregory Nicola. So make sure you keep in touch with us. Subscribe to our Twitter. It's one of the best way, as well as LinkedIn, to stay in touch with NeuTiger. Everybody have a good weekend. Professor Jha, thank you so much.
Thank you.
And goodbye.
Bye.